Hi everyone, this is Jason Marks from NI, formerly National Instruments, and I'm here to talk to you guys about testing machine learning systems for ADAS and autonomous vehicles through advanced simulation. So my role at NI is I am the Americas-based business development manager for autonomous vehicles. I'm located in San Francisco, California. I've had the pleasure of working with a lot of companies on their advanced simulation projects, particularly tier ones and OEMs, around how they're approaching testing autonomous systems, particularly around stressing perception systems accurately through simulation. So today we're going to talk a little bit about the architecture of autonomous systems. This may be review for many of you, but it's good to paint the context around what we're going to talk about when we talk about how we simulate the appropriate inputs into that software stack. We'll talk about approaches in general into validated autonomous systems. Then we'll talk specifically around what's unique about ADAS and AV systems and how that relates to simulation that's different from testing other ECUs and other software stacks on vehicles. And then we'll talk about particular simulation workflows as it pertains to model in the loop, software in the loop, and hardware in the loop, and how that ties into your simulation strategy. So diving right into the system architecture for ADAS and autonomous systems. A lot of you have seen a multitude of permutations of this type of slide before, I'm sure. But what's unique about ADAS and autonomous systems is the sheer number of sensors and the volume of data that's being moved through those sensors into your compute systems, and then the amount of energy that those compute systems have to do to figure out what's going on in the world. So effectively, we've seen systems with 10 plus cameras, 16 ultrasonic systems for doing things like parking assist, radar systems for doing automatic emergency braking and other level 1, level 2 systems, LiDAR for doing level 3 and other level 2 systems and doing classification as well, and of course cameras for detecting the world around you. But all those sensor data sources are being transmitted into the autonomous compute hardware, whether that's a distributed system, a centralized system, or a hybridized system that has compute on the edge and compute centralized. But they all follow the same robotics paradigm of the sense, plan, act, or perceive, plan, control. That namely that there's a high bandwidth number of sensors coming into the system that are representative of what a driver may see of the world, or the autonomous driver would see of the world. It computes them, makes a decision on how to act, and outputs controls to actually drive the vehicle around, whether that's to just keep you going on a normal day's drive or to make an advanced maneuver to try to avoid crashing. What's unique about these autonomous systems is they really are supercomputers. So they're really systems that have a high number of compute elements inside of them that have to compute this perception algorithms, the planning algorithms, and the control algorithms on board them. In addition to that, there's a large number of, as you add more compute, you fight against the energy of the vehicle. So if you have an electric vehicle that has a 100 kilowatt hour battery and your autonomous vehicle compute hardware takes over a kilowatt of energy, well, then you've reduced your entire driving rate by 1% just by having an autonomous system on there. So thermal and power performance considerations are critical here. So a lot of optimization is occurring to make sure that these systems are both automotive grade ready and are capable and are not going to reduce the amount of driving miles that you can do based on that system. So taking a look under the hood of this system, we see that there are a number of things that are within each of those elements of that sense, plan, act, perceive, plan, control robotics paradigm. Within the perception stack is where a lot of the machine learning algorithms reside. So namely, you receive information from your cameras and your LiDAR system, mostly to do a lot of this machine learning algorithm work. And you do things like detecting where the lanes are, detecting what objects are in the scene, where they're going to go next, detecting what those objects are in particular, detecting what's part of the scene is the road, what part of the scene are stoplights, what part of the scene are moving objects, what part of the scene are static objects like buildings and trees. And then you have to detect where you are in the scene based on the information you can get from your LiDAR systems, from your stereo camera systems, from your GPS systems. After you've figured out what you think the scene is, then you send that information over to your planning system. That has to decide what the best maneuver is to make based on the given situation is. So there's some potential machine learning that could exist within behavior selection, but most of these are heuristic algorithms. Once that planning system is capable of saying, hey, I think this is where you need to go next, it then sends a trajectory over to a control system to figure out how to actually execute that trajectory. So that's a series of steering, brake, throttle kind of commands and algorithms to actually drive the vehicle. So what's interesting to note here is that within that perception system, you may see a lot of GPUs, neural net accelerators, machine learning algorithms that run there. The planning system, you may see CPUs and FPGAs, real-time CPUs, and in the control system, you see largely FPGAs and ASIC systems for actually doing that system. So a mix of different computational accelerators to actually compute these things. And what's also unique here is that this is never the same for any two OEMs or tier ones based on the number of sensors, the type of vehicle, the operational domain that vehicle executes in, the type, the cost requirements associated with this. So you'll see different requirements, different hardware on board these systems based on the requirements of the particular application at hand. What's also interesting to note is that if you take a look into some of those perception algorithms, those algorithms in the perceive bucket there, they could have any number of different permutations of those algorithms. They could have early fusion, which is a concept that you could receive both camera and LiDAR information and cascade that information together, send those through the algorithms, namely the convolutions that simplify and the deep networks that actually do the detection, and then you could get a certain output. Likewise, you could send it through a different algorithm that takes camera and LiDAR separately and sends them both of their own convolutions, both of their own series of algorithms, and then compares the output of them before. So this is a great representation of a paper from Berkeley that actually talks about different mechanisms you can use to do detection of objects, to do detections of the scene. And there is no consensus on what's best. Different algorithms require different hardware, different accelerators, different software implementations, and require a little bit different of a process for validation, particularly when you need to talk about synchronization of different inputs. If you need highly synchronized inputs, if you're going to do early fusion where you're cascading those two sources of data together in the exact same frame, but you may not need the same level of synchronization for those inputs if you're doing them separately and then comparing the outputs afterwards. So a lot of different requirements come from different kind of methodologies that people are using to actually implement some of these algorithms on their perception systems. So that brings us perfectly to validation. How do you go about validating those autonomous systems that are machine learning based or non-heuristic? They could calculate outputs in 1 millisecond, they could calculate outputs in 10 milliseconds. They could spawn a decision that's accurately the right decision, everybody agrees, or it could just spawn a decision that nobody knows what the right decision is. And even more so, the perception system might fail, but that means that the planning and control system that subsequently happens has to still operate appropriately in that kind of use case. If the 0.001% that the perception system is unable to calculate, it means that the planning and control system needs to be robust enough to handle that system, handle that failure. So what do people do in OEMs and tier ones? Well, a lot of you guys are very used to this type of kind of approach. We see the majority of validation happening in simulation. That means that we simulate inputs into our algorithms to do model in the loop. We simulate inputs into the systems to do software in the loop. We simulate synthetic data sources into our ECUs to do hardware in the loop. But a lot of that validation happens, the majority of that validation happens in simulation. We use Waymo as a great kind of proxy. They always talk about they have 15 plus billion miles of simulated road data. They have 15 plus million miles of road data themselves. So that's a good kind of 1,000 to 1 ratio of the amount of work that's being done in simulation versus other. But in addition, there's a lot of other areas where system validation is happening. So a lot of companies equip road vehicles with recorded sensor suites that are streaming raw data into them that they can then later play back in the lab. And that's a source of data for called a playback hill. And then there's people that actually integrate all these things together and do a synthetic hill where they take the synthetic source of data from a simulation and they then play that into an ECU, get a real-time response from that ECU, and then drive the vehicle around in the simulation. So NI's approach to this is to cover all those bases there. NI is in general a simulation agnostic company. So we don't create our own simulator, though we do partner with a number of simulation companies that are experts in their domain. One of which I'll talk about today is called Monodrive, a company that NI is invested in and is very proud of their high fidelity physics-based sensor emulation, which we will talk about here in a sec. But we partner with a lot of different simulation companies to provide that simulation source, and we will work with whatever one that you are used to working with, ANSYS, IPG, Veras, you name it. In addition, that we try to cover the entirety of the bounds for system level validation for autonomous systems. So that includes, like I talked about, recording, playback, hardware in the loop, the validation of the hardware itself, and the production test of the hardware itself. So jumping right into the simulation topic at hand, I think that there's a number of challenges that make high fidelity perception system simulation very hard. It's been well known how to do physics-based vehicle dynamics simulation for a long time. That technology has been around since the 1940s. And we know a lot about how to stress control systems, how to stress planning systems. There's a lot of fantastic companies that are really good at that. But what makes ADAS and autonomous systems more challenging is that you have to stress their perception systems, and those are non-heuristic, and those require a large amount of data source. And they are actually you have to create a representation of a real-world sensor in a simulated environment. So what that means is you have to create a high fidelity model of the particular sensor that's going to go in your vehicle within a simulated environment. That's really hard to do because there's so much that goes into the physics of creating a sensor. There's so much that goes into noise of the world in creating a sensor that you have to accurately recreate. So if you imagine that the energy you take to put into a high fidelity sensor to incorporate that physics, to incorporate that validation of that sensor, and any errors that are associated and noise that are associated with that sensor, well, that usually requires a whole lot of complexity in computation. So your simulation systems may be 10 computers, 20 computers, 30 computers deep of high performance processing in order to get these images and these frames generated in real time that can then stress your system in real time. So you have this battle of fidelity versus computational excellence of your system. So a lot of the high performance, high fidelity sensor simulation systems that we've seen require many, many computers to actually accurately model these sensors and to do that in real time. And on top of that, once you have a system that's capable of doing a high fidelity sensor model in real time with the appropriate computational resources, well, then it becomes a question of how do you address your test coverage within your operational domain? How do you deal with the fact that you live in an infinite state space and you need to cover the test bounds within that? Simulation lets you do that to a large extent because it's just that simulated. But there's a lot of really interesting strategies being employed for actually giving you that test coverage. A lot of companies and a lot of research papers that are happening right now to actually cover that test coverage. We won't talk about that in length, but that's the key next element once you solve these two problems. So a typical simulation architecture looks as such. It's going to look very comparable no matter who you're working with. There's some simulator that exists. And within that simulator, there are models that reside in that simulator. So that simulator is the worldview. It could be Unreal Engine based, it could be Unity based, it could be based on some other type of physics-based engine that the particular simulation vendor is building. There's an ego vehicle, which is a vehicle that is to be tested with the software running on it. In that vehicle, there's actors, which are other vehicles, pedestrians, motorcycles, dogs, cats, cows, you name it. And then what you have to do, so the fidelity of that actual simulator isn't really what matters. What matters is the fidelity of the sensor you place in that simulator. So the response you get from that simulated sensor has to be accurate to the response you would get from a real life sensor as well. That's the challenge with high fidelity sensor simulation. Once you've got that capability, you place the sensor in that physical location on that ego vehicle that can then drive around the vehicle. The next challenge is streaming that data over to whatever you're testing. So if you're testing just the perception algorithms, what you want to do is you want to stream information from the camera LiDAR systems that are physics-based representations of those sensors validated to be accurate to those sensors, get the response into this perception system, get the response from that perception system, which will be a classification of the world. And then you want to compare that classification against the ground truth, the semantic information of that scene. And you could do that because you're working with a simulator. You're working with a simulator, and simulator has ground truth associated with it, so you know what every single data point is. One of the challenges with using real life data as your source of data for testing your algorithms is that they're typically human annotated, and human annotation has failures. I mean, it's never going to be 100% perfect. There are occlusions, things that it doesn't know. The simulator knows everything because it's created that synthetic world for you. So you have the synthetic information to test. That's if you're testing the perception system, you compare the output of the perception system against the semantic information in the simulator. Now, if you're testing the entire control stack, what you need to do is you need to feed those same type of perception algorithms, so those same sensor models that are validated into the perception system. They need to then compute the entirety of the stack, and they'll output a drive-by-wire command back through the system to drive the ego vehicle in the simulator. And to do that in real time, again, requires a lot of computational excellence, a lot of data movement that needs to happen at really high data rates, and there's a lot of strategies used to employ that. If you want to test just the planning and control system, you would feed an ideal version of the world, an ideal sensor of the world into the planning system, and then it would then execute those same things. That's a lot less computationally expensive because you're not generating those synthetic sensor models. So in those sensor models, what we see being the most important parts of having a high fidelity kind of world is that you have high fidelity physics for physics-based sensors for radar, LiDAR, camera, ultrasonic. And then you have some representation of GPS, IMU, and wheel RPM, which is usually the other input you need for a lot of these algorithms. In a conjunction with the physics-based version, the high fidelity version of those sensors, you often want to have a semantic version of those sensors as well, because that lets you compare the response you get from your algorithms to what actually is in the simulator, what is the ground truth of that system. So you may be asking, well, why do I need high fidelity sensor models? It seems like a lot of computational energy when I can test this with ideal versions of those sensor models. And the answer is in a lot of examples. We use radar as a great example. Radar has some unique properties associated with it where there is an analog to digital converter, an A to D, that has a signal to noise ratio, an SNR, associated with it, where if you point a radar at a really big reflective object, it will get a huge number of returns to that radar that will wash out anything that it sees on a small that's much smaller and gets smaller returns. So the signal to noise ratio of the particular A to D on the radar and the way the antennas are built on that radar means that if you have something like a fire truck on Highway 101 in front of you, you get a huge number of returns if it's really reflective. Versus if you have a couple of small cars or cones trying to direct you away from a fire truck, those would be much smaller and those reflections would be much smaller. And you may not actually see them, you may not be able to detect that it's time to move it, and you may not actually make the maneuver you need to make. And that's important that you stress those type of things in simulation before you go into the real world, because obviously that could result in a crash. Now, radar in particular is fairly interesting because there's a lot of things associated with radar that changes the way that it responds that are physics-based, namely the material properties of particular objects and the way that 77 gigahertz radar reflects off those material properties will be different depending on whether you're looking at concrete, whether you're looking at metal, whether you're looking at plastic, and what color they are. Those matter significantly. Same thing applies for camera. Same thing applies for 905 nanometers or 1550 nanometers for LiDAR. So all those material properties, all of those characteristics of the sensor electronics, they need to be simulated to get a response that's representative of how that sensor is going to respond. The next piece of this is even if you get a physics-based representation of those sensors, well, that doesn't solve all the problems. That gets you 90% the way there, but real-life sensors have real-life problems. They're not all perfect. So what you have to then do is go and validate that the sensor model you've created is tuned appropriately to represent the sensor that's actually in real life. And there's a lot of ways to do this. You could, besides just implementing the physics, you could use deep learning to train those sensor models. You could use chambered environments to characterize the radars, the LiDARs, the cameras. You can take a lot of measurements with them in real life. You can back engineer the models, but every single company you talk to from a sensor model provider, you should be able to ask this question: what is the way that you validate sensor models? And they should be able to answer this in a way that proves statistically that they're actually accurate sensor models. Well, once you've got a sensor model that you trust in a simulation environment that's capable of generating these in real time, then the beauty is that you can iterate through all of the parameters in your operational domain to cover your requirements. So different weather conditions, different road deterioration, different maneuvers, these are all fully capable of being created in simulation once you've got those capabilities. And then you can really start stressing your system. So that brings us to how do you scale? Well, if you have your requirements for a specific operational domain, you can create parameters within that operational domain that says, hey, I want to run these different scenarios, these different NCAP scenarios, let's say, these different weather conditions, these different roads, and then you want to deploy them to the cloud. You want to say, hey, batch those simulations in some Dockerized containers, deploy them to some number of instances, execute them, and then give me results. So this is what lets you do these millions or hundreds of millions of miles tested per year to actually, once you start deploying to cloud resources. Again, a fairly complex way to do it, but this is how you get to that scale that simulation lets you do that other types of testing do not let you do. One thing additionally I'll add is that, some unique capabilities of simulation that some simulation companies provide is the ability to create digital twins or real to virtual environments from a pre-recorded drive into a synthetic world. So that means that if you encountered a specific scenario in the real world, then you can recreate that digitally in a synthetic world. And that lets you have the opportunity to really iterate on those encounters you happen in the real world. Hey, I almost had a crash. Let me see what my vehicle would have done if it was raining instead. So you get the opportunity to do that. Additionally, this gives you another opportunity to place a real sensor in the real world, a synthetic sensor in the synthetic world, and compare the outputs and tune the synthetic sensor so that you get the output that you would expect to see as validated. So the last thing I'll talk about is how do you take that information and transport it into a hardware in the loop system? Because we talked about model in the loop and software in the loop. How do you make that into a hill loop? Well, the big difference is that you have automotive interfaces, you have network interfaces, you have camera interfaces that you have to address that are high bandwidth and low latency. So you need to have, first and foremost, the ability to talk to those particular interfaces. Second of all, you need the ability to actually inject the appropriate data in real time into those interfaces. So what that ends up looking like is you need to take data that's being available in your simulator as fast as possible, inject it into your hardware in the loop system in a deterministic fashion, re-timeline everything because latencies will be adjusted based on the different sources of data, and then inject them appropriately into the ECU with things like rest bus simulation, AutoSAR compliance, fault insertion that you may add, get a response from that ECU, run your vehicle dynamics systems, and send that back to the simulation platform so that it can then iterate through the next step. That all has to happen within one frame cycle. A lot of strategies associated with that. Don't have time to talk about that today, but that is a very complex thing to do, and it's very computationally expensive to do this process. And one thing that it scales into is if you had the requirement to test all of the ECUs in a distributed system, it would be an entire room of testers. And we've seen this actually deployed at customer sites that they do an injection system for their ECU, they do an over-the-air system for their radar, they do an over-the-air system for their camera ECU, yada, yada, yada down the line. And it creates this massive block of different types of simulation platforms and different types of integrations for hardware in the loop to do all this. The last thing I'll end on is that NI cannot do any of this stuff alone. We are a test provider that has knowledge of how to kind of how to architect these tests and orchestrate these tests. But there's so many complex elements of this that requires partnering. So in particular, we have simulation partners I mentioned, MonoDrive, ANSYS, IPG, Carson, yada, yada, yada. We have providers that have data storage, data movement. We have providers that do things like automotive networks like ACA and ETOS. File formats, sensor processing, yada, yada, yada down the line. Many of these systems that we put together end up being 6 or 7 companies working in conjunction in order to actually deliver these solutions. So that's all I had. I'm happy one of my colleagues will answer your questions. I unfortunately cannot attend given the early nature of the timing, but I'm thank you for joining and happy to be a resource that you can all reach out to me on. Appreciate it, everybody.